Hey everybody, this is going to be a video about panelizing a PC board in Kicad using a Python script. Now, if you've been following my LED project at all, you notice I've been promising to make a 1/18th scale police car, and I've been trying various ways to point-to-point wire some WS2812s into a light bar, and nothing ever really worked out very well. And I finally decided that I needed a printed circuit board. So I got busy and learned how to lay out a printed circuit board on Kicad, and came up with some boards. But they're really small. They're really tiny, some of them. And I realized that the only thing I had to do is panelize the PC board so I could get a decent sized board, not waste a whole bunch of real estate, and get some boards, some quantity out of the deal for the money. So panelizing was a necessity. So I panelized 3 sets using just doing it by hand, and putting about 20 PC boards on a panel. And after I did the first 3, it's pretty tiring. I was really tired of doing it. And then that was using the WS2812. Since then, I found a smaller version, which is the SK6812 Mini, or it might be called the Mini 3535, depending on where you look. And they're 3.5 millimeters square, whereas the WS2812 is 5 millimeters square. So had to start again, redo all the footprints, redo all the PC board layouts, and redo all the panelization. Well, I didn't want to do the panelization again. It's really tedious to do by hand, so I took the time to work out a Python script that would do it. Now I looked on the web, and there's a lot of stuff out there to do panelization, and either I didn't find exactly what I wanted, or I couldn't understand the code. And mostly I couldn't understand the code, and I wanted something I could work with myself. So I decided to do it myself. So this script, the way it works is really simplistic. It's really procedural. It's just do one thing as I thought of it. Do the routing lines, figure out where the board origin is, create a new board, plop it on the thing. It's just kind of a linear procedure without any smarts. It doesn't do any board translations. You can't pack your boards together. Some of them are horizontal, some of them are vertical, to make the best use of space. This just lays them out in rows and columns, and that's it. And that's good enough for these boards. And it won't handle a board with cutouts very well. So, but basically it's a simple thing. It's easier to read than some of the ones with a lot of classes and everything. You have to follow what's going on. So anyway, I'll just go through this and show you how I did it, and maybe you can use it. And maybe if you're new to Python, this maybe can help you learn a few things about Python. Okay, let's go through this Python script real quick. I'm using Python 2.7.3. The first thing we do is make a little template for our graphic line that goes in a Kicad file. And where this comes from is just a PC board, a PCB file in Kicad, and this is the format of its graphic line. It just says the start position XY, the end position XY, the angle, which is always leave at 90, the layer that this appears on, in this case it's edge cuts because this is the board outline. Excuse me, and the width of the line. This 1,000th ensures that you know where the board house knows where the center line actually is. So and all this script does is read files, write a file, and manipulate strings. There's no special Kicad interface or API or anything like that. As far as this Python script knows, it's not doing anything with Kicad at all. It's just manipulating strings and writing files. So that's what our template does. It echoes that graphic line, except wherever X and Y appear, we've substituted it with the string X in braces and Y in braces. And for the layer name, we substitute name in angle brackets and the width in angle brackets. So we're going to use this as every time we want to write a graphic line, we're going to use this and modify the values. So our board param function is called when the program starts up. And we'll take a real quick look at that. This is a Python idiom for, this is a standalone program. If name equals main, it means this is the first script or the only script in our script, and the program starts here. And all this does is check that you've entered the right number of arguments. You want 5 arguments for height, width, the number of rows, number of columns, and the path to the PC board file. Now, if it passes that, it just goes and calls the board param and substitutes all the arguments in for that call. So here we are receiving our arguments. We set our height. Since these are all strings, we set them to actual floats or integer values. We got the height of the board, the width, the number of rows, number of columns, and the offset. Now the offset is a fixed number, and I've just decided to start the board at the top left corner at 50 by 50 millimeters on the PCB drawing. Added to that 50 millimeters is 10 millimeters for an empty handling area for any machines that handle the panel. And then I add 1.27, which is the radius of the drill diameter, the 1 mil drill diameter. So that gives us an offset of 61.27 millimeters. The number of boards are just rows times column. And here we have some Python lists that are going to save some data for us. We set the origin, X origin, Y origin to our offset that I just explained. Here we set some values that help us lay out the routing line. And this A, B, and C are referred to here in this little diagram. Our origin is here at Y origin, X origin. The A point is right here. This is the first route segment. It's a short route segment for the first PCB. Then it leaves the gap for our mouse bytes. And then point B starts here and covers across 2 boards, 2 PC boards. If there was more PC boards, this BC line would be continued here for as many PCBs as we have. And then for the last PCB, we have a last origin point of B point, and the length is calculated from the A value. So that gives us our main 3 types of routing lengths. And we do the same thing in the vertical direction, but I didn't draw that in because once you understand this, you can understand the vertical. Now the next thing we do is lay out our horizontal routing. We take our line template. We use the regular expression module from Python and use the sub, which is a string substitution function. We pick up line T here. We substitute F silks, because this is going to be on the silk screen layer, for name. And we substitute 0.001 for a width. Now, y for the y value is going to be the same for a horizontal route. So we just put in our y origin for y, for the y value, the two y values. This writes to both of them, the start y and the end y. And now we begin actually filling in the rest of the line by going through it. And the first line, as I said, is the short from origin to A segment. It's only done once. And we substitute our X origin for the first X. And the A, we get the A from by adding our X origin to A, and that's be our next X value. This one here in the argument, you notice we didn't have it up here. This wrote both Y positions in our template. This is going to only write the first X when we have the one argument tacked on here. So X origin will go into the first X, and this value will go into the next X. So that keeps those two separate. And then we want to remember where we are, the last X position, and then we want a pin that's a complete string, that's a complete GR. Where'd it go? It's a complete GR line string now, all filled in. So you want to save that, pin that to route lines. Now here's a little oddity of Python you have to pick up. If you make a variable A and say A equals 1, then when you print A is equal, it'll print 1. And then if you make another variable and say B equals A, and you print B, it'll print a 1. Now if you go back and change A to 2, but don't change B, A will then print 2, and then if you print B, it'll print 2. And that is because when you sign B equal to A, it's just a reference. It doesn't take the value that A is. It takes the reference to A. So you're always referencing A. And that happens with lists in the same manner. So if I appended without this bracket and colon closing bracket and just had RTE, when I appended that to route lines, it would go in there and it would be the string we just built. The next time I come through, or even down here, when I finish building this line and I said RTE equals is appended to route lines, both strings and route lines would be the same as this. Just like B printed 2 when you changed A. Now there's two ways to handle that. There's a module called copy, and it makes shallow copies and deep copies. You'll have to read the documentation to differentiate between those, what those do and what you need when. But there's another way with a list. When you this is called a slice, and without an argument in front of the colon and after the colon, it references all the elements just automatically for you. It's kind of, you don't have to say it starts at 0 and ends at whatever. You can just say, do it this way, and it includes the whole list. What this is a string, but in Python it's a list of characters. So when you say this, when you use this little expression right here, it does make a copy. It makes a copy of the list and puts it in route lines. And then when you come down here and you do the same thing, it's going to be the new, it makes a copy of the new string, and so you don't have that problem of the same string ending up in your list of lists here. Route lines is a list of lists. So okay, I hope that's clear. You can look that up and play with that in Python. And you just have to remember that this is what happens. Okay, now we've done our first little short line. That first little piece did this line here. Now we want to do this one. And for multiple PC boards, this would repeat instead of just be up here one time. So that's why this is in a loop. And for the number of PCBs we have, -1, or the number of columns we have, -1, would be the number of PCBs in the column. We do the same thing, substituting the appropriate X position for each X. And we save that. We save that to route lines, and then the last one does the last short line and saves it to route lines. Now when we finish that line, we want to remember Y0, the Y position, in this case, for every horizontal line. And that's going to help us calculate where our board PCB origin is going to be. And we save that to the board RC list. Modify Y0 here for the next routing line. It's the height of the board plus the drill diameter. Then we build a new template till it's an F-silk 1/1000th line width, and we put our 2Y values in for this row. And then we repeat for that for every board. And then at the end, we have one routing line too many because all the PC boards are surrounded by route lines. So the last one we don't need, so we just pop it off. Okay, now for vertical routing, it's exactly the same thing, except we're going the vertical direction. And when we finish a whole line, we save X. We save the value of XO in board RC, and that's going to give us our points for the board for PCB board origins, and advance XO by the width of the PCB plus the routing diameter. And it's the same as before, and the little pop is necessary here too because there's one more routing line than boards. Next we want to do the panel outline, and that's pretty straightforward. We start at 50/50, and then our width is the number of columns times the width of our board plus the routing diameters plus 1127. That's the blank empty 10 millimeter handling area plus half of the routing diameter, and similar for the board height. And then we substitute those boards in their XY values for top left, top right, bottom left, bottom right. We make a template like we did before on edge cuts this time instead of the silkscreen, and we put all those lines, we draw all those lines around our board panel, and we save it in panel outline. Now here's where we calculate our PCB origins for every position that we want a PCB. We just go through the board RC, and we take every X and pair it with every Y, adding adding the drill radius each time. Okay, now we're going to call our Gen PC board and finally write some data to our file. We need to pass in the file path, the number of boards goes to num PC, board lock is our board locations, it goes into X_Y. These are all the points of origin for all the PCBs we're going to write. And the panel outline goes to outline, and route lines goes to routes. First thing we do is pre-compile some regular expressions, GR line and XY. This really helps, especially for mod. You don't have to keep writing these regular expressions all the time. Mod has 4 different regular expressions it looks for. That's segment, at, with a digit, a GR line, and via. And if we look in our PC board file, this is the current file with the PCB you first draw and lay out. We see that we have our segment lines, and we look, and that has 2 XY positions for start and end. Our via has a single XY for a point. GR lines we looked at, where is it? GR line we looked at before. It's got start and end XY points. And if I go to a find module here, well, here's our at line we want, and it has a point for every module. This is like the LED or a capacitor or what have you, and it's got 1 XY point. So those are the lines we're going to look for to change in order to place our PCB in the correct location. And we're going to use, for that, we're going to use NX and NY. And we set those to a real high value because we're looking for the smallest value they can be. We want to make sure it first compare succeeds, and we drop it down to some point within the PCB on the board. So that's why they're set to real high value. And here's where we do that. We just loop through the PCB file, and every time we find a smaller X or a smaller Y, we save that in NX and Y. And we end up with, this should be the top left corner of the board outline for the PC board on the drawing. The next thing we're going to do is just read the PC board into a list so that we have all the data available and we don't have to keep getting it off the file. We don't want to keep reading the file. That's kind of a hassle. And if we have it in a list, we go through it each time we want to generate a new PC board and modify the contents of this list instead of reading the file. So that's all we're doing here. That ends up in source PCB. And now we just want to generate the data for our new PCBs. So for each PCB we go through here and find our search for mod line. That's the one that searches for the 4 types of line we want to modify. We do an if feature. We look for at, GR line, segment, via, see which one it matched. We end up setting up the values and passing it to modlock, which is going to modify the location of every feature on the PC board. And the way that works, modlock is down here. It receives all this data. It subtracts our NX, NY. That essentially makes the data we have, all the coordinates relative to 0.00, and then we add our offsets for X and Y, and that effectively moves everything to where it belongs in the panel. And we keep calling that for every line that has a XY point in it that we need to modify. And then we do all that for every PCB in our file. So now we're finally ready to write all this data. First thing we do is open our file, seek to the end, -3 positions. What this does is skips right in front of the last character in the file, which is a unmatched closing parentheses. Let's find this guy right here. This parentheses right here has no corresponding opening parentheses, and I'm pretty sure they use this for an end of file marker. At least that's what I assume, and it seems to work out that way. So the first thing we do is write our destination PCB file that puts all the PCBs on the board. Then we write our routing that we've calculated, and that puts all the routing lines on the board. And then we draw our panel edge with the outline list, and that writes the panel. And then we write the closing parentheses back and close the file, and that's it. And if we've done a good job, done everything right, it should work out. And so let's go look and see if it does. Okay, now I'm going to demonstrate using this script on my 4-light PC board. This is a straight copy from the original PC board I made up. I copied it to a version with a panel in the name so I can differentiate it from everything else. You don't need the dimensions, so I'm going to delete those. And I discovered while doing this video that there's a bug in the program. If you leave the original PCB in the plane of the area that the panel is going to fall in, it's going to move some routes randomly, and I'm not sure what it is. I'm going to look and see what's going on. I think as long as you keep the board well out of the way, 50 millimeters is around about this area here, so this is well out of the plane. I'm going to save that file and then go run the command. Open our file back up, and our panel should be there, and there she is. Now we don't need the original, so you can just delete that, get it back in the neighborhood. And there's our 5 rows, 3 columns, routing lines, routing lines are in, the mouse bites go here, here, all these gaps in the middle. We turn off the board rat's nest. So it looks like it did a pretty good job. So yeah, that's pretty useful for you. I hope it saved me hours of work. And just be sure that you keep the board you're copying out of this plane, vertically and horizontally. And I'll try to find what that problem is, and I'll change the code. The code's available on the referenced website, and if you see the version jump up, hopefully it'll be the fix that fixes this problem. Okay, so here's the example of the board I got from OSHPARK. It's the 2-light one we just laid out. This one I hand laid out, but the other two, the 4-light and 8-light, they're currently being built, and those were laid out on with the program we just looked at. But this guy here is gonna hold 2 LEDs, and if the camera would focus, you could see I messed up the footprint, and hopefully it can be I can rig it where it'll still work. But here's the LED. My camera's just refusing to focus on anything. It's a Canon. I want you to know it's a Canon. Can't focus on something stuck right in front of it. So one LED will go there. Oh, look at that, man. I apologize that you can't see this at all. Maybe I'll back out, it'll do better. So one LED will go there. One LED will go over here. In the center are 4 holes for power, ground, data in and data out. So these are going to be daisy chained together. And this is the Mini 3535 or the SK68 12, I think, whatever you want to call it. And so it's the 3.5 millimeter square. And just to compare it, here's a regular WS2812. Put next to it, you can see it's a pretty good difference. Definitely smaller and going to work a lot better in this application anyway, if I can get them soldered to the board. So anyway, that's it. Hope you enjoyed it. Learn some Python, learn some Kicad, and have fun. We'll talk to you later.